So now, before we keep going ahead with some of the new material in the course, I want to kind of take a step back and do a little bit more review. The topic I want to look at here is something that we covered, or would have been covered in quite a bit of detail in your foundations course, and that's to talk about acids and bases. And one of the reasons we need to get back into this is eventually where we're going in this course is we'll be talking about reactions of organic compounds. And a lot of reactions of organic compounds, the acidity or basicity of the compounds involved ends up playing a big role. And so we're going to kind of be looking at this, some things that we've seen before when it relates to acid and base strength, but we're going to be coming at it in a much different perspective. And what I really mean by that is, if you remember in foundations, we did a lot of the qualitative, the non-mathematical stuff with acids and bases. But then we also spent a lot of time doing calculations. So in this course, we're more worried about the non-mathematical stuff. So some of those things like pH calculations and buffer calculations, all that stuff, we're really not going to be doing those types of calculations very often in this course. What we're going to be more worried about is sort of the general trends, the general rules, and how it relates to some of the functional groups we just learned. So we want to start by reviewing what is an acid, what is a base. And hopefully you recall we had two different definitions of that. Bronsted and Lewis. The Bronsted-Lowry definition dealt with it from the perspective of protons. It said that an acid was a proton donor, whereas a base was a proton acceptor. And then we said more often, especially in organic chemistry, we use this other definition, the Lewis definition. And it's not that the Lewis definition is better or more correct, but when we're talking about reactions in chemistry, what is it that determines whether a reaction takes place? Reactions are all determined by electrons. Electrons make up our bonds, and so it's as bonds form, as bonds break, that's all related to the electrons. So the Lewis definition gives us an acid-base definition based on electrons. And it tells us that an acid is an electron pair acceptor, and a base is an electron pair donor. Now, are these definitions 100% consistent? The answer to that is almost. So, if a compound fits under the Bronsted-Lowry theory, or the Bronsted-Lowry definition, then it also fits Lewis. So in other words, if a compound is a Bronsted-Lowry acid, it will always be a Lewis acid. And if a compound is a Bronsted-Lowry base, then it will always be a Lewis base. However, we can't say the same thing in the other direction. So there are Lewis acid bases that are not Bronsted-Lowry. One of the most common examples we talk about is the compound BH3. So boron, you may remember, being in group 13, is one of these exceptions to the octet rule. It only has 6 valence electrons. Because it only has 6 valence electrons, it has an empty p orbital. That empty p orbital means that it's able to accept electrons. It wants electrons. So, since it's an electron pair acceptor, it fits as a Lewis acid. But if something is donating electrons into it, BH3 doesn't give up a proton, so it doesn't qualify under the Bronsted-Lowry definition. Now, most acids and bases that we'll work with in this course will fit under both headings, Bronsted-Lowry or Lewis. But we just want to be aware that there are some that only fit the Lewis definition. So recall, and this is something you probably saw in Foundations, that any generic acid can react with water to form a conjugate base, conjugate acid pair. And then we learned, we're not going to go back through the math here, but that the pKa is equal to the negative log of A minus times H3O plus over HA. And so we learned that for a strong acid, and remember we use that term very loosely, strong, because it's a relative term. But the stronger the acid is, the more of it's going to dissociate. If more of it dissociates, then A minus and H3O plus, the conjugate acid conjugate base pair, are going to be in higher concentration than the acid itself. And that ends up leading to very small pKa's. For a weak acid, the opposite is true. Less of it dissociates. And so it's HA that's in higher concentrations, and pKa will end up being large. Now, we want to be careful. We want to remember that this scale is logarithmic. And so even pKa 7 versus 8 is a 10 times difference. it's also important for us to talk about something known as the leveling effect. And that's because you may recall in foundations or any type of general chemistry course you might have taken, we said that NaOH was a strong base. And the reason we were able to say that is anything stronger will just react with water to form hydroxide. So when it comes to things that take place in water, hydroxide is as strong a base as we can have. And again, that's because if you have a stronger base than hydroxide, it's just going to react to form hydroxide as soon as it gets added to water. But that's one of the things that makes organic chemistry very different. In organic chemistry, we use many solvents that aren't water, and many solvents that are much less reactive than water. So it's entirely possible that you could talk to someone who's an organic chemist and they tell you that sodium hydroxide is a weak base, and 2 minutes later you talk to an analytical chemist who, in their field, everything they do works in water, and they tell you sodium hydroxide is a strong base. And then you're left wondering, who's telling me the truth? And the irony of that is that both of them are. It's all about the solvent, all about the perspective. You probably also learned in general chemistry or foundations that something like HCl or HI is a strong acid. And it is. But again, these aren't the strongest that exist. And so for acids, there exist such things as this one, and you may not be able to read that real well, it's pretty small. But yes, the name of this compound is magic acid, and whereas HCl has a pKa of about -7, magic acid has a pKa somewhere around -22. So we're talking about more than 1 trillion times stronger than HCl. And HCl is pretty strong. With bases though, if you've ever worked with sodium hydroxide, you may know that it's a very, very stable molecule. It can just sit in a bottle on your benchtop or on a shelf, and it'll survive for years. Nothing will happen to it. Now, sodium hydroxide is the conjugate base of water. Water has a pKa of about 16. A little bit less, but just rounding here. Well, that's nothing compared to this. So what you're seeing here in this video is a substance known as tert-butyllithium. And after the video is over, I will draw its structure for you. And here we go. You can see it's in a syringe, and as soon as it gets pushed out of the syringe, it immediately catches on fire. And I can tell you from experience, I've worked with tert-butyllithium. There is nothing fake about this video. It is that reactive. So the structure of it, it's this 4-carbon molecule with a negative charge right here. It's the conjugate base of this molecule, which has a pKa of somewhere on the order of 60. So we're now talking about something that's 10 to the 40th times stronger than sodium hydroxide. So again, just an illustration that when we talk about strong versus weak when it comes to acids and bases, these terms are all very, very relative. And so in many cases, that's really what we're worried about. What we're most concerned with is if we're looking at two substances, which one's the stronger acid or which one's the stronger base? We're not always as concerned about with this one has a pKa of 12.3 and this one is 13.2. That doesn't always matter as much. What we're more concerned with is that we can figure out which one's stronger. And so are there trends that allow us to predict acidity or basicity? And the answer is yes. I also want to remind us, we know that pKa is used for acid strength. What do we do for base strength? So there is such a thing as pKb. It does exist. And, well, nobody uses it. Why does no one use it? Well, we don't use it because we have the pKa scale. And why use two different scales to describe two different things when we can use one scale? So if we have a strong acid, we're going to think about this in the Bronsted-Lowry definition. A strong acid is one that just wants to get rid of those protons. And so if something's a strong acid, after it gives up those protons, it's going to form a conjugate base. Does it want those protons back? And the answer basically is no. If it's willing to give up those protons that easily, it doesn't want them back. So a strong acid always leads to a weak conjugate base. The opposite is also true. If we have a weak acid, it doesn't want those hydrogen. It doesn't want to give those hydrogens up. And so the conjugate base that it forms is generally going to be strong.